Hi, Madison Crowns. This is M doesn't want to look at the camera. I'm going to read chapter 18 sections 1 through 4 and chapter 19 sections 1 through 4. I'm going to go over bolded words, give the gist of stuff. So, yeah. So, chapter 18 section 1 is about the electric battery. Galvini discovers that brass and iron, when put into a frog, makes the leg contract when there's electric charge running between it. And then he found other metals could do that. Volta doubted that it was life force or animal electricity, so he did more experiments. And he had unadvanced technology, but he discovered all this really advanced stuff. And right. So then he discovers moisture on the contact points between the two metals is what is helping it conduct the electricity, and then, he finds that the simplest battery contains two plates or rods made of dissimilar metals. One can be carbon, called electrodes. So the dissimilar metals are electrodes. The electrodes are immersed in a solution, such as a diluted acid, called the electrolyte. See those bold words? Right. So then, in a dry cell, the electrolyte is absorbed in a powdery paste. Such a device, properly called an electric cell, and several cells connected together is a battery. Although today, even a single cell is called a battery. Okay? Then the simple cell, in figure 18.4. Yeah, that one right there. Use the diluted sulfuric acid as the electrolyte, and one electrode is made of carbon, the other of zinc. That part of the electrode remaining outside of the solution is called the terminal. The connections to the wire circuits are made here. The acid attacks the zinc electrode and tends to dissolve it. But it leaves two zinc acids, and then it's like how it requires negative charge, and then more ions into the solution, causing more charges, and so on and so forth. Alright, and there's some more pictures of batteries. Then section 2 is called the electric current. It talks about how when continuous connecting paths are connected between the terminals of a battery, we have an electric circuit, as seen in 18.6. Simple circuit. And then there's a symbol for a battery. Over here is the wire. The electric current in a wire defined as the net amount of charge passes through it per unit time at any point. Thus, the average current I is defined as I equals delta Q over delta T. Here's the example problem. Okay, enough example problem. Then here's sections 2 example problem. It is, as you can see, a concept one. There's some more circuit battery things. Yeah! Okay, and here's the last little bit. So, when we speak of the current flowing in a circuit, we mean the direction positive charge would flow. This is sometimes referred to as conventional current. Awesome. Ohm's law, resistance and resistors. I hope I said that, but I probably didn't. Okay, so it was George Simon Ohm, who established experimentally that the current in a metal wire is proportional to the potential difference V applied to its ends. So I more or less equals V, or I think that's the symbol for Team Aqua. So, okay. And here's example explaining it. Yeah. Okay, so when it's defined as resistance, so that the current is inversely proportional to the resistance, we combine this with the above proportion. We have I equals V over R, where R is the resistance of the wires or other devices. V is proportional to difference across the device, and I is the current flow through it. This relation is often written V equals IR and is known as Ohm's law. Okay, many physicists would say it's a law. It's not a law, but rather a definition of resistance. Good for them. Ohm's law is so ingrained that we won't quibble with continuing this usage, as long as we keep in mind its limitations. Materials for devices that do not follow Ohm's law are said to be non-ohmic. Okay. See figure 18-19 for definition of resistance. Here it is. I'm going to turn this. I'm sorry, guys. I know it sucks. Okay. Yeah. Tilt your heads at an odd angle. Here's another equation. R equals V over I. Okay. Because R equals V over I, we see an ohm is the averted Greek alpha capital omega, because R equals that. Okay. The unit for resistance is called an ohm. Okay. Here's the example problem. Example! Yay! Okay. Resistor. In many circuits, particularly in electronic devices, resistors are used to control the amount of current. Resistors have resistance from less than an ohm to millions of ohms. Here's some more figures and stuff. Okay, resistivity. Okay. Indeed, it is found experimentally that resistance of R, the metal wire, directly proportional to its length L and inversely proportional to the cross-sectional area A. That is, R equals PL over A. Resistivity, and so where P is constant of proportional is called resistivity. That depends on the material used. Here is the example problem. Yay! This video is gonna be like over 10 minutes long, and I'm sorry, but I cannot do it by myself and have it last. Okay. Starting of chapter 19, section 1. Resistors in series and in parallels. So, when two or more resistors are connected end to end, as shown in that figure, they are said to be connected in a series. Okay. Here's the equation for adding up the voltage of a series and finding its rate of flow. Ooh, fun. Okay. Now let us determine the equivalent single resistance R. The draw of the current is a combination such as a slight let V by V equals IR. We equate the expression with 19-1. That equals that, and that. So that's a series. What is it? Another simple way to connect resistors is through a parallel where they all line up like that. And so then you just add all of the I's together to get total. So that's parallel. And here is how you use voltage and resistance to calculate all of that. There's more and more examples, and that is for the inverse or one, and yeah, okay. Here's the example problem, yay! And more of that. excellent. Yay. Okay, here's an example for the section 2. You're gonna have to remember it. Well, make you remember all of sections 2 example problems. Wahaha. I'm an eye. Here's sections 3. I'm also gonna make you remember that one. And section. Oh, almost fell off the bed, Em. Be more careful. Okay. Sections 4 example problem. Okay. Now we're here. Okay, a device such as a battery or an electric generator that transforms one type of energy into an electric energy is called a seat or a source or electromovement force of EMF. Okay. The symbol, weird looking E, is usually used for EMF. Don't confuse it with E for electric field. Got that? Okay, well okay. For one thing, charges must flow between the electrodes of batteries and flow between electrodes of batteries, and there is always some hindrance to completely free flow. Thus, a battery itself has some resistance, which is called internal resistance. Okay. Well, we must measure in terminal voltage. Okay, since this resistance R is inside the battery, we can never separate it from the battery. The 2 points A and B are diagrammed representing 2 terminals of the battery. What we must measure in terminal voltage, which is VAB. Here is VAB equals EMF minus IR. There's it again. I don't know the difference. Okay, that's example 9. Time for Kirchhoff's rule. Okay, Kirchhoff's first or junction rule is based on the conservation of charge. So at any junction point, the sum of all currents entering the junction must be equal sum of all currents leaving the junction. Kirchhoff's second rule, or loop rule, is based off the conservation of energy that states the sum of the charge is potential around any closed path of a circuit must be 0. Okay, then the decrease in voltage between the 2 ends of a resistor is called voltage drop. Here's Kirchhoff's loop rule formula. Yay! So when it decreases, we write that, then we write that, and that. Okay? Oh, this is section 3, by the way. Kirchhoff's rules. Okay. Section 4. Solving problems with Kirchhoff's rules. I'm going to call him Christoph, if I have to. Okay, so when we use them, we find it might be useful to designate currents in each of the separate branches given by current in a different subscript, such as I subscript 1, I subscript 2, and so on and so on. This figure shows an example of that. Here is a long thing about solving it. But since this video is almost 15 minutes long, I'm going to just show it to you. Okay, so we're all done. Bye. M, who's almost fallen off multiple times while I've been filming this, also says bye. And Zabel, who's been a little whiny pants, also says goodbye. Okay.